Hello, in this video I'll be going through the latest version of the automatic VTNA calculator, where I have made some improvements, bug fixes, and added a few features. So this is just an add-on to the previous video, but I would like to inform you that the paper is now available in digital discovery, and it has been improved through the review process. So I'll have a link in the description of the video. To access the second version of the automatic VTNA calculator, you can go to the link in the README file as before, and then from the Google Drive you download the file, and I'll skip to that now. So once the download is complete, you can double click the GUI application, which will generate a console shown here in the background with some information, as well as the GUI itself. So this is the second version, and the main differences are that I've added a same access button, which I'll be speaking about, and also separated the VTNA and VTNA with score to separate buttons to more easily obtain overlay plots with or without the fitting function used to derive the overlay score, as I discussed in the previous video. Another change I've added is that if you input a dataset which has some errors with it, then you will not be allowed to start a calculation. So this prevents the app from crashing and informs the user about what needs to be addressed, for example, negative data points or inconsistent column titles in the input data, as I described in the previous video. So to show some of the new features, I will input some data from the kinetic investigation of the azamichael addition between piperidine and dimethyl itaconate, which I've mentioned in the previous video. And the link to the publication by Clark et al. Is shown in the description of the video. So I can import this using CSVs. I could do it separately, but I can also do it in one go, which will give me these experiments where the names come from the name of the CSV file. So if we want to visualize the data, you can click kinetic data, and it might be useful to set it to the together mode. But this should be similar to in the previous video. So if I look at the initial concentrations, you can see that experiment 1 has initial concentrations which are higher by 0.15 molar compared to experiment 4. So experiment 4 can be considered a same access experiment, and experiment 1 as a standard experiment, which means that we can select 1 and 2, and then dimethyl itaconate, the reactant, as the output species. So you need to use a reactant for same access analysis, and then you can simply press here, and you'll get the same access overlay plot, where the same access experiment, which is experiment 4, has been shifted horizontally to start at the concentration profile of the first experiment, and you can see they're overlapping, which is as expected because you don't have product inhibition of the reaction, and it's not a catalytic reaction. So to show a more complex reaction system, we can look at the kinetic dataset on the intermolecular catalytic asymmetric bromoesterification reaction studied by Lancaster and Braddock et al. This dataset was also mentioned in the previous video, and you can see the link to the relevant paper in the description of this video. The dataset consists of a standard run and then different access experiments where the initial concentration of one reaction species is altered, for example that of the catalyst or of the carboxylic acid reagent, as shown in the previous video. The authors also carried out same access experiments with different initial concentrations compared to the standard run, and then product and byproduct spiking experiments, which have the same initial concentrations at the same access run 1, but also added product or byproduct or both with an initial concentration corresponding to the difference in the standard and the same access runs. So because these concentration values are given in millimolars, I will change the concentration unit in the setting. Then we can simply click on the standard and the same access experiment use the carboxylic acid as the output species to generate the same access plot. So you can see from from this plot, there's no overlay, which tells us that either catalyst decomposition or product inhibition is occurring. So to find out which of these is actually true for this reaction system, the authors added the product and the byproduct to the same reaction, which gives us overlays. So this means that the catalyst is being inhibited by either the product or the byproduct, and to distinguish between these two, the same experiment was then carried out, but only with product spiking. So this gives us poor overlay again. There's no inhibition of the catalyst, and the same excess experiment is quicker. If we spike the byproduct into the reaction mixture, you get overlay, and this is the evidence that the authors use that this catalytic reaction is being inhibited by the byproduct. Lastly, to show some of the data cropping features, I will open this data set here, which is also mentioned in the paper. It's on the gold catalyzed 1,3-O transposition of Ynones, and you can see it in this paper here, which is linked in the description of the video. So if we first open this data set, we can visualize the data as we did before. You can see the concentration profiles have many data points because it's from an in situ IR experiment. So to speed up the calculations, it might be useful to lower the data point density. I can do that by clicking crop data, and then in this frame I can reduce the number of data points by a selected factor, for example 5. Then I can say evenly with respect to time, or it could be with respect to one of the reactants or the product. And you can see now that the data point density has been reduced. We can also do a total VTNA calculation for this dataset, which was done in the work leading to the Auto-VTNA publication. Apply quick settings so that we don't have to wait too long. And this gives the orders shown in the box on the bottom right. We can then can't visualize the results because they're 3 normalized species, but we can generate overlay plots with these order values to see that you indeed get concentration profile overlay and also linearization with these order values. We can also generate the VTNA overlay plot with the score. So that I just click the button on the side, which gives you this plot, and this is similar to what I showed in the previous video. And to modify these plots, you can go on the settings here. Lastly, I'd like to show some other functionality in the cropping data window. Since we have a dataset with high data point density, the default is to use range mode. Previously, we reduced the data point density by a factor of 5, but we can also remove entire ranges of data points. If we have percentage set in this box, we can remove selected ranges in percentage values, for example 30 to 70% of the reaction times for each experiment. So if we now visualize the data, you can see that this range has been removed for each of them. So removing data points in the middle of each concentration profile might not make all that much sense, but we could also remove all the data points that occur after 50% of the reaction time, like this, which would give us truncated concentration profiles. We can also remove data points in the beginning, and if we do this, the time axis will be shifted as long as we have this checked. Lastly, I'd like to just make it clear that you can also apply these settings that I've been mentioning to different experiments separately by using frame number 1 and number 2. So in this video, I've described the second version of the automatic VTNA calculator, which is similar to the previous, but with a better layout, improved user friendliness, same excess functionality, and also an improved data cropping window. I hope you found it useful, and if you find any bugs or have any ideas for improving either the Auto-VTNA Python package or the graphical user interface, then please send me an email or create an issue in the GitHub repository. Thank you very much for listening.